talk about some basic integration techniques, and this is reviewing what we've done so far in this calculus class. Nothing is hard, but sometimes things look like they're the same, and they're not. So let's look at the first couple of examples. So I have three integrals that look basically the same, but they're not. So let's look at the first one. And in my toolbox, all of the weapons I have to do integration, when I see something that is a quotient, and the numerator has a lesser degree than the denominator, I always think, oh, please let it be a natural log. And in this case, it is. So if I make my u equal to x squared plus 4, I can say, goody, this means du is equal to 2x dx, and so I almost have that. So I have 2 times the integral of 2x dx over x squared plus 4, so this is just 2 times the natural log of x squared plus 4 plus c. And this is optional whether you want to put those absolute value signs around it, because x squared plus 4 is always going to be positive. Well, cool. And then I have my second one, which I'm looking at, and I think, well, if I brought that 4 out front, that would look like an inverse tangent, where my u is equal to x and my a is equal to 4. So this would be, excuse me, my a would equal 2. So this would be 4 over 2 times the arctangent of x over 2 plus c. Our two arctangents of x over 2 plus c. Well, I'm feeling really good about all this stuff. And then I get to this one. Well, you know, here's the thing. I have equal degrees in the numerator and the denominator. So the only thing I can do whenever I have equal degrees is I'm going to start by doing some long division. And I'm going to divide by x squared plus 4. And when I do that, I get 4 up here. So that means that when I subtract, that gives me negative 16 as my remainder. So this is actually the integral of 4 dx plus or minus 16 times the integral of dx over 1 or x squared plus 4, because this is negative 16 over x squared plus 4. Okay, I can do that. This is just 4x, and we've just done that problem basically. This is going to be negative 16 over 2, the arctangent of x over 2 plus my c, which will give me 4x minus 8 arctangents of x over 2 plus my c. So 3 different problems done 3 different ways. But they all have the same denominator. Okay, let's look at this. Well, this example is sort of different, and I'm going to use the distributive property to really look at it. So if I looked at it this way, looking at two different types of integrals. The first one is really a power rule, because if u is equal to 4 minus x squared, du is equal to negative 2x dx. So I'm going to put a negative 2 in there and a negative 1/2 on the outside. So basically this integral is just u to the negative 1/2 du. So if I integrate that, that's going to be, adding 1, I'm going to get u to the 1/2 divided by 1/2 times negative 1/2. So that is just going to be the square root of u. So this part is just negative the square root of u, which is 4 minus x squared, plus, well now this one looks like an inverse sine, which indeed it is. My a for this one is equal to 2, and my u is equal to x squared. Now remember, the inverse sine is the only one you don't have to say 1 over a times. So this one is going to be 3 inverse sines or arc sines of x over 2 plus your ever popular c. So we will add that. Ah, how lovely. Well, let's look at this a minute. This is 1 plus the cosine of e to the negative 2x times e to the negative 2x dx. Well, if I were to do that, I would distribute. And I get a e to the negative 2x dx plus the integral of the cosine of e to the negative 2x times e to the negative 2x dx. And I'm going to take a deep breath. Now, for this one, if I let e equal negative 2x, that means du is equal to negative 2 dx. So I need a negative 2 here, and this is a negative 1/2. So whenever I integrate e to the u du, that just gives me e to the u. So this part is negative 1/2 e to the negative 2x plus my c. Now let's look at this one. This time it is the cosine of e to the negative 2x. So I'm going to make my u e to the negative 2x. Well, that means du is equal to e to the negative 2x times negative 2 dx. So I need a negative 2 up here, which means I'm going to have a negative 1/2 out front. And then what my integral looks like is negative 1/2 the cosine of u. Well, the integral of the cosine is the sine. So this part becomes negative 1/2 the sine of my u, which was e to the negative 2x plus my c. So when I write all of this together, I'm going to have negative 1/2 sine of e to the negative 2x plus c. So obviously I've put together a whole bunch of ideas in that one problem. All right, I look at that, and I'm going to say, well, you know, the derivative of x to the 6 is not x squared. However, if I were to look at this as x cubed squared, the derivative of x cubed would be 3x squared. So I'm looking at that and thinking it's really an inverse sine function. So I'm going to make my u to be x cubed. So du is equal to 3x squared dx. So I'm going to put a 3 up here and a 1/3 out front. So now what I have is 1/3 the integral of du over the square root of 16 minus u squared. That means my a is 4. So this one, inverse sine again. And remember that some of us like the arc sine better than the inverse sine. The u is x cubed. So there is my function. Now all of this has been rather straightforward. Nothing too bad has happened. All right, this one looks like, oh my goodness, if it's an inverse tangent, I'm good, but otherwise I'm not in good shape. So what I'm going to do is I'm going to look at this, and I'm going to look at this as a perfect square. The c that I would add for the perfect square is half of 2, correct? Is 1, squared is 1. And 1 plus 4 is equal to 5. So this thing really looks like this. Therefore, my u is going to be x plus 1. My du is just dx. My a is equal to 2. So when I look at this, this is really the integral of du over u squared plus 4. And this would be 1/2 the inverse tangent, or arctangent, of u over 2 plus c. Well, that's 1/2 of the arctangent of x plus 1 over 2 plus c. And that looks pretty good, I think, so far. And there's your homework for the first part of this lesson.